Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in this video I would like to look at common drain amplifiers, which are also known as source followers because they basically act as voltage buffers. Let's take a look at one of the web pages by my colleague Jennifer Hassler, in particular the FPAA virtual machine tool site. If you scroll down a little bit, there's one particular point where you can find some slides on experimental setups. And here, there's a nice summary of a couple of 2-transistor amplifiers, and particularly the sort of source follower that we're looking at. It's shown here in the INFET form. And the exponentials here may look a little strange if you're used to seeing MOSFET formulas that have squares in them, but Professor Hassler likes to operate her MOSFETs in the sub-threshold regime that is not off, as most books call it. Current does flow in the sub-threshold regime, and if you're assuming that the current going through one MOSFET is the same as the current going through the other MOSFET, you can equate those currents, and that's legit because the current doesn't have anywhere else to go. Then you can derive this formula that says the output current is equal to the input current minus what here is being called Vref times the parameter kappa. Notice it's assumed here that kappa is the same for both transistors. If the kappas were different, you could probably derive an appropriate formula for that case. Let me start up my Mac port of the RASP tools. This is a work in progress. When I get this a little more polished, I'll release it publicly, but right now it's fairly rough. In the meantime, you can try doing all of these examples using the Ubuntu image that Dr. Hassler's group provides. Okay, so let me pull up my NMOS buffer example. I believe I created this example by starting with one of the built-in examples, namely a simple single transistor circuit where you just measure the current coming out of an INFET. If I recall correctly, I took that example and then added another transistor. And for some reason, it's being a little odd. It's insisting that I have this big blank space at the top and the bottom. Not sure why that is. Anyway, let's take a look here. Sometimes when things load in, they come in oddly. So I'm going to take this battery and rotate it back into position. There we go. Notice that I have the bulk connected to the source up here. On another occasion, we could try connecting the bulk to ground and see what difference that makes. The connection here looks a little awkward, but when I tried to clean it up, it broke things. Basically, Xcos is very picky about making connections, and if you don't make them in just the right order, it complains at you. So if I get something that works and connects, I tend to just leave it, even if it looks ugly. So I'm going to start by setting the kappa of my transistors to 1. So hopefully we get a nice input-output relationship. Let's see, for VT0, let's use 300 millivolts. I think I've seen that a lot. And we have 50 nanoamps for our threshold current, which is the same for both transistors. And that formula I showed you earlier, if you had transistors with different threshold currents, you could create an appropriate modified formula for that. All right, so it's going to be a little strange, but I'm going to set Vref to 0. Every time I change the voltage here, it turns this sideways. Don't do that. I want this vertical. So that's Xcos for you, or at least this version of it. Anyway, it feels incredibly odd to me that I can set the gate to 0 volts and the source to 0 volts and still get a current through here. To my general intuition, this should not work, but I guess we are in this weird sub-threshold regime. So with that in mind, let me hit simulate and see what pops out. It looks like I have a really beautiful curve here. So I have a perfect input-output relationship in terms of being a perfect voltage buffer, more or less. I have a slope of 1, which matches having that kappa. And the fact that it starts at 0 here matches up with picking Vref to be 0. So let's see what the simulation gives me if I put in a Vref of 0.5 volt. If I simulate that, we now get a new curve. that looks like the curve we just had, except now everything's offset a bit. It doesn't start sloping up until we hit a voltage input of around 0.5 volts, although it does start sloping up a little bit beforehand. So that's interesting. Now I wonder, oh, it turned it sideways again. I'm not going to fight it. Can I put minus 0.5 volts in here and get something meaningful out? That feels really counterintuitive, doesn't it? All right. Yeah, okay, here we go. Now it's starting with an offset of 0.5 volts, and it goes up this direction and, of course, rails out when it hits 2.5. Wow, that feels very strange to me. I wonder what would happen if we actually put a load here. Remember that this is assuming we don't have any load, so whatever current is flowing through here is flowing through here, and by those formulas, this must be an absurdly tiny current. So this may be one of those things where it simulates but wouldn't work in real life. Leave your opinion in the comments below. All right, let's try a different kappa. So what I'm going to do is I'm going to set the kappa here to 0.7 and the kappa for the other transistor to 0.7, so those match up. And what I'll do with the voltage reference is let's set that to 0 again. All right, so with that all in mind, let's hit the simulate button. Simulate, simulate. All right, so it is starting at 0 again with VREF equals 0. And when we get up to 2, it looks like the voltage output is around 1.4, maybe a little bit less. Let's see. Let me zoom. So we have 2. Oh, pretty close to 1.4. It's maybe a smidgen less. I don't feel like thinking about it in much more detail than that. Anyway, it's pretty much a slope of 0.7. So there you go. So if we go back to the slide deck on Professor Hassler's website and scroll down a little bit, we see that there is a PFET version of this source follower. So we basically change the NFETs to PFETs and swap where we're placing the bias and the input. So let's try that. So let me pull up my PMOS version of the buffer. Now my VREF is going to be referenced to VDD, which is 2.5 volts. So I'm setting my VREF to 2.5 volts, and that should be equivalent to setting VREF to 0 in our NFET version of the circuit. And I've set all of the kappas to 1 volt. And let's see, I should probably set the threshold voltage here. There you go. I think that's realistic. All right, let's press play. And look at this. We have this really nice input-output relationship. It is a true buffer. Let's see what happens if I change this to 2 volts. Why does it do that? Why does it want to keep turning things sideways? Anyway, let's press play on that one, and we get something that looks like, oh, we don't get anything that looks like anything. It does not want to simulate that. There we go. It's the simulation problem. I love this. Oh, come back. Come back, tooltip. Anyway, it does not like it. There we go. IDA Calc IC. The residual routine. Why does it not stay? Or the linear setup or solve routine had a recoverable error. Come back. But IDA Calc IC was unable to recover. I love that. Recoverable error, but unable to recover. This is the standard thing I get when Modelica is unhappy for reasons I don't know. What if I do something absurd like change this voltage to 3 volts? So this is equivalent to setting the reference voltage to minus 0.5 volts in the NMOS example. Let's see if that will simulate. All right, so let's hit run, and then we get something that looks like this. So like one of the examples we saw earlier, it starts sloping up at around an input of 0.5 volts. So that's kind of interesting. Let's see. Let me set this back to 2.5 volts, and let's try a different kappa. So here I'm going to set the kappa to 0.7, and I'll set the other kappa to 0.7. All right. So let's try that out, and hopefully that will simulate happily. And I get something like this. Wait a minute. Why is that working so well? That doesn't feel right to me. Okay, this is 0.7. This is 0.7. And that's looking really nice. Why is that looking so good? Why am I not getting a slope that's less than 1? Huh. Let's see, what happens if I were to set this to 3 again, just for fun? Yeah, that still seems to be working pretty well. Let me change this back to 0 again. Sorry, not 0. Let me change it to 2.5. Is there something magical about the PFET version of the circuit that is an issue with the NFET version but isn't an issue with the PFET version? Let me take the kappa here and set it down to 0.1. And we'll, of course, do that to the other one. So this should give me a very, very, very tiny slope. What in the world is going on here? Oh, I do see a little bit of change in the curve at the very end here, but it pretty much has a slope of 1. Now, if I try the same thing with the NFET, let me go pull up the NFET one again. Let me close out the PFET. Okay, here's that NMOS example again. And in case you can't tell, this isn't planned. I'm figuring this out as I go and inviting you to join along. So welcome. All right, so I've changed the kappas for the NMOS example to 0.1. And if we run that example with that very low kappa, then I get what I expect. I get a really, really small slope. So why are we having this issue that we expect with the NMOS version, but we don't with the PMOS version? That's extremely strange to me. Usually there's parallel issues in the NMOS and PMOS versions of a circuit. So if you have a clue as to what's going on here, please let me know in the comments below.